And welcome to Physics in the AM. We are in progress right now. Team Vector. Um, Conservation of momentum, a new concept, second one in our conservation unit. The main idea is, and it's frozen here, but I've got it on. Total momentum before, total momentum after are equal. We're using a simulator, collision kart simulator, because we do not have the actual items any longer in school. We're going to have elastic collisions and inelastic collisions. And I want to explain them right now. We'll learn by watching, observing, and measurements what makes a collision elastic and what makes it inelastic. Have any of you actually ever heard of elastic collisions versus inelastic? It's not a common thing outside of physics. Okay, you may have. So, with an elastic collision, you can think of pool balls too. The pool balls are all approximately the same weight. Right? So this, we're going to be changing weights. So the first setup that we have on your paper is one where we've got a kilogram and a kilogram, same weight. And I'm coming in 3 meters per second on it. This one's at a standstill. What's going to happen? And some of you might have more experience actually with pool balls, this is why I bring this up, than with hearts and stuff. But if one's at a standstill, and you hit it dead on, what happens to the red card when it hits the blue card? The red card stops, what happens to the blue card? Okay, and they're the same mass. This is why I'm talking pool balls. If you've never played pool before, fine. Now this is when pool balls hit dead on. At angles and stuff, you get slightly different things, and they both move and they glance off each other. But this is a head-on kind of collision, one at a standstill. So, I have the variables noted. Okay. Really, what we're going to observe is that this one stops. This one continues trucking at the same speed the other one is. Okay? Now let's just watch this and see, and then we'll do some calculations. Okay. So let's see here. I've got this at 5. I had 3. Okay. This one I'm going to have at 0. And I have the masses matched. Okay. I'm doing elastic collision. Let's start. Not that exact. Okay. As predicted, right? You've seen this before, probably. Right? Let's take a look at some of the math behind this, okay? Okay, total momentum before, total momentum after. I'm using A and B to be the cards. The red is A, the B is the blue. Okay? V1 is the first speed before, and then 2 is the after. So let's just fill in the numbers and do the math behind this. So we've got 1 kilogram times 3. You're going to get a real one. You're going to do this too. That's V1A, 3. And I should be using 1.0 just so I have 2. Okay. Now I'm not putting anything down for MB, V1B because it's 0. Hey, Ro. Come here. I've got your sheet. On the other side, MAV2A. Second speed turns into 0, so I'm not going to include it. So MV, also 1 kilogram. B2B. How do we solve it? I know we have the answer. We're pretending we didn't know this. Now, you guys know how to do the algebra. You divide by 1. 1 times 3 on the left side, divide by 1, and you got 2. Okay? Now, I didn't think the algebra would be tricky. We start easy, we work up from here. So what I'm going to get you guys to do is the next scenario, B. And I'll do the visual after. So, you guys see what I'm talking about. What if the red card is 3, the blue card is 1, so it's more mass on it. And V1 for the red card is 3, the other one's 0, standstill. Let's make a prediction before though. What's going to happen? You've got a heavy card coming in to hit. Okay. It's a good prediction. They'll both be moving. They'll both be in motion, is what you're saying. Okay. Can you guys, using those, and I have a V2, B of 4.5, can you guys do the math? And this time, you'll have 2 chunks to the right-hand side. Can you guys do that math while I set this up? And I'll join you in progress. Okay? I'll stop the recording while you figure out the math. Now we're at various spots. Some people were done right away. Some people are just plugging away at it. So we have do the multiplying, then the adding afterwards. You're going to have 9 minus 4.5. I'm going to just skip to this part. Okay, when I do this, you get 1.5. So this means it's still positive, so it's still going to the right. But this means that, as predicted, it will hit, they'll both be moving. The heavier object will, it's basically like being rear-ended by a car, right? And if you're a heavier vehicle, the one vehicle will go darting out a little faster, the lighter one. The other one will continue rolling faster. That's without applying brakes. But anyways, which is totally crazy. Let's just see as some of you finish up. So I'm going to reset. Go to 3. And what was the other one? So mass 3. I'm keeping this at 3. I think this was the setup, right? Okay. 3 and 1. So this one looks more massive. It hasn't added on. So we should see this. Rams into the blue guy. So it's still rolling slowly, right? Okay. That's exactly as predicted. Next. And some of you have actually worked ahead and calculated this next one. Oh, I did the wrong one. So the same kind of calculation here. what happens when the other one is, so here's what's happening here. We still have more mass for object A, and it's traveling at 1 meter per second. Object B, the blue card, is lighter, 1 kilogram, 3 kilograms versus 1 kilogram, but it's traveling towards it at -2. So I'm just changing one thing. What do you think happens with V2 for the red? This. Well, we can calculate it, then test it out. I'm going to quickly jot down the calculations. Okay, so what does that mean? The heavier cart was going slower. The lighter cart was going faster, but in the opposite direction. And they hit, right? Here's one way to think about this. They're on freezer. Okay. The initial momentum of the red cart is 3 kilogram meter per second. The initial momentum of the blue cart is -2, opposite direction, kilogram meters per second. So the red cart still has more momentum, right, when they hit. Does that make sense, first of all? Okay, it's going to be transferred on. Let's watch what happens. According to this, opposite direction. So, I got this set up. Let's run it through. So, approaches. Wow! Go opposite direction, right? If they were the same mass, same speed, they go backwards. Is it possible to have different masses, different velocities, and one stands still after the collision? Yeah, it's mathematically possible. We can find the right combination. They would have to have the same momentum when they hit. That's the whole thing. Can you guys suggest a way to have a heavier red cart and a lighter blue cart hit each other? Well, can you guys make some suggestions? How can I make them both the same momentum when they hit? Give me a combo. Remember, this is sticking to 3, 2, and 1 for the masses and for the velocities. Yeah. Sorry. Okay, so here's what I'm going to do. So here I have initial velocity for the red as 3, or 1 and 3. So what if I did the opposite here, and I made this, I got to reset. What will happen here, guys? The blue has the same momentum coming in as the red. They both have 3, opposite directions. What do you guys predict will happen when they hit each other? Okay, there's a prediction. Hey, let's see what happens. Ah, they just switch. The initial momentum, they were equal and opposite, and then they just transferred the same amount of momentum transferred to the other, right? And they just switched directions. Okay. If they somehow locked in the middle, like think of train cars that have a connection or whatever, then they would stop. Okay. Okay, I've slipped down. Okay. That's that first thing. Are we okay with this? Because I got more. Elastic collisions, I think you might notice, bounce off of each other. Momentum is conserved. Momentum is conserved in what we call inelastic collisions. And inelastic collisions Here's why they're different. They actually lock together after. Okay? So with an inelastic collision, that would be like what I was describing. If you can imagine two train cars that hitch together and they have some hitch, something like this, that locks in place when they hit each other, okay? And most realistic collisions are, other than pool balls are pretty close to 100% elastic collisions. Most other collisions, car crashes and collisions, you have some form of elastic and inelastic. It's somewhere in between. Because maybe the car bumper of yours, they lock in with the side of the next car and they kind of travel together as one object a little bit, and then they separate after. So it's somewhere in between. We do the most idealized, easiest to calculate stuff. It's still the momentum before equals the momentum after. So the equation hasn't changed, except for the fact that after the collision, you guys are stuck together. Okay? So we just have it as one mass and only one speed. I call it V2 for both AD. We could just call it V2 if you want. Let's do the calculation for this one and then watch. So what I'm saying is that MAV1 is 1 kilogram. V1 is 3. Plus MV 1 kilogram. 0. MA plus MB, so I can add this in 2 kilograms. Stuck together. We're trying to find V2. Now, mathematically, that's fairly easy. 1 times 3 is just 0. I got 3 divided by 1. Mathematically, I've solved this. What does that mean? So the red card comes in, the blue card's sitting still. They lock together for some reason. They travel as one object after, and they keep going in that forward direction. It's slowed down, though, because that same amount of momentum is now shared with twice the mass. Does that make sense? It slows down. That would be like me in my roller chair. There's too much friction with the wheels. But it shall cost me a heavy medicine ball right now. Would you guys expect me to move? Catch it? Yeah. Cool. And then I roll back with the medicine. My feet aren't touching. I had a really good system of rollers. I would roll back for quite a while. The only reason why I stopped is friction, right? That obviously isn't an example with the same mass, but let's just take a look here. While you jot that down, check in here. Let's go to the collision center. Reset. I'm going with inelastic collision. With an inelastic collision, what did I have mass-wise? I forget now already. 1 and 1 kilograms. I went 3. Okay. This should verify our calculations. So they're going to stick together and keep moving. But the speed's cut in half because it's twice the mass. Make sense? Okay. Take a look at the second scenario I have B. 3 kilograms and 1 kilogram. So the red's 3 kilograms, 1 kilogram. B1 is 3 meters per second. What do you predict will happen when they stick together? Still moving which way? It'll be faster than in A, but it'll reduce the speed, but it'll not reduce as much. Yeah. It'll keep moving to the right. This is like a heavy truck hitting a small car at a red light or something. Okay. Do the calculations. I'll set this up. I'll just set it on right now to watch. I think the arithmetic and the algebra isn't too tough. Should get an answer of 2.3. Okay? 2.25, but this is round. Okay? So make sure you can get that. So set this one up. That's rounded from 2.2. Let's use our imagination to make a prediction for C. So red is still 3, blue is 1. Red is moving at 1 meter per second, but blue is moving at -2. So it's moving towards it. And faster than absolute value of velocity. Now, you look at their individual before momentum. The red will have 3 times 1. It'll have 3 kilogram meters per second. The blue will have 1 times -2. It'll have 2 kilogram meters per second. So without even calculating, which way will it move after it's hit, right or left? Is there more momentum in the forward direction or the negative leftward direction? It'll keep going forward. Okay. You guys do the calculation for that? It'll slow down dramatically, though, because I'm asking you to. And you can do the calculation. I'll set it up. I'm trying to find these. I know it's going to be possible. And I'll set it up right while you're working it out. And we'll watch. Okay, now this time I have the right thing set up. Should come out to be a quarter, as predicted. 0.3 because this uses round, but yes, decimal 2. Okay. Slowly trudging forward. Positive direction. Okay, you guys get that? Now explosions, it's not necessarily an explosion, but we're going to say both carts are pushed off from the middle at the same velocity. So think of this. V1 is 0 for both objects. They're stuck together. We have a 2 kilogram cart and a 1 kilogram cart stuck together. There's a force that pushes them apart. I said it different. M1, the together mass is 2. When they separate, it breaks into 2 equal pieces, 1 kilogram, 1 kilogram. The one is going -10, the other one is going, don't know. Okay, let's figure this one out. This is really the same equation, though. The momentum before, it's just that it's all one lump. Okay? M1 is 2 times 0, so I'm going to just put 0. MA, 1 kilogram. V2A, -10. And we solve. So that's going to be 10 divided by, you guys see this, right? 1. They should be equal and opposite. I just don't have the space here. make sense? Okay. I don't normally give, by the way, M1, because it is really just A plus B. Okay. So I'll often give it that way, or I might give the total mass in the mass of one of the chunks that blows off. If you think of a rock with a stick of dynamite in it, goes two different directions. It's the same kind of thing, an explosion. And so they go off at the same, as long as their masses are the same. This second one, the masses aren't the same. So I'm going to start it off. So 0 on the left side because I'm going to start changing the mark. 0 on the left. Second masses, A and B. 3 kilograms. MA is just M1. Oh, MA? Sorry, which one are you talking about?
The one is after
Oh, yeah, MA, M2A, yeah. M1 is actually the sum of A and B. Oh, doing the wrong thing. And I'll finish this off and then we'll be done. Okay, mathematically, that's 10 in the negative direction divided by 3. Right? Not me. I was going to see if I could fit this in on the video thing. So I'll see if we can fit that in. I'll take